So far in studying rotations, we've looked at translational quantities like position, velocity, acceleration, and we found analogous rotational quantities. So instead of position, velocity, and acceleration, we have theta, the angle, omega, the angular velocity, alpha, the angular acceleration. The equivalent of mass is moment of inertia. The rotational equivalent of force is torque. And then we found we can write the kinetic energy, 1/2 mv squared for translational motion. The equivalent for rotational motion is 1/2 I omega squared. So we found rotational equivalents for basically every type of quantity we've studied for translational motion, except for momentum. So in this video, I'm going to look at the rotational equivalent of momentum, which is called angular momentum. And then we'll use it to solve a couple of different types of problems that are tricky to solve without the concept of angular momentum. So one way we can approach this is we can look at the formula for linear momentum, P. This is actually a vector quantity, so I'll just go ahead and do this. The vector P equals the mass times the velocity vector V. So we can just translate this into rotational variables. We know that the rotational equivalent of mass is moment of inertia, I, and the rotational equivalent of velocity is angular velocity, omega. So we get a rotational momentum that we call angular momentum, and we give it the symbol L, which is L equals I omega. This is angular momentum. So we can just multiply the moment of inertia I by the angular velocity omega, and we get the angular momentum L. That is one definition of angular momentum we're going to use, but I want to be a little bit more sophisticated about this. So I'm going to do this. We have an equation. We can write Newton's second law in terms of momentum. And Newton's second law in terms of momentum looks like this. The force F equals the derivative of the momentum with respect to time. That's an equation we came up with when we were looking at momentum. So what I can do is I can just take the cross product of a vector r with both sides of this equation. I can take r cross f equals, well, let's just take r cross both sides of this equation. And remember, the vector r is a vector that connects the place where the force acts to the origin of our coordinate system, or to the center of rotation. So let's say we have some coordinate system, x, y. We have a force F that acts at this point, and the vector r connects that point to the center of this coordinate system. So this is our vector r. The center of our coordinate system here is the center of rotation. Okay, so there's our vector r. So let's do this cross product. Well, on the left side we get r cross f, and on the right side I'm just going to move that r inside of the derivative here, and I'm going to say this is d by dt of r cross p. Well, r cross f, that's just torque, and r cross p we can define as our new angular momentum. So this is our other definition of angular momentum, L. This gives us an equation that is analogous to F equals dp dt. Gives us an equation that looks like this. Torque equals dl dt. This is all summarized in this slide. The angular momentum can be defined about any point. So I can pick any point in an xyz coordinate system and define the angular momentum about that point. All I need to know is the distance from that point of some particle with a momentum p, and I can take this position vector r and calculate the angular momentum as r cross p, the cross product of this position vector with the momentum vector. So the angular momentum L is defined as r cross p, And I can think of this as r perpendicular times p, or r times p perpendicular. So it's either the component of p that is perpendicular to r times r, or the component of r that is perpendicular to p times p. So for example, in this diagram here, I have this vector r, and say this describes the position of a particle here with a momentum p. Well, the angular momentum I can either think of as the perpendicular component of r, that is the component of r that is perpendicular to p, times p. So I can say L equals r perpendicular times p. Or I can think of this as this position vector r times the perpendicular component of p. This is p perpendicular here, the component of p that is perpendicular to the radial vector r. Either one works just fine. They're both consistent with this definition of the angular momentum as a cross product. So that's one definition of angular momentum, and then I can write Newton's second law relating the torque to the angular momentum. The torque is just the derivative of the angular momentum with respect to time. The definition we're really going to use more often, though, is this one. We're going to think of the angular momentum, L equals I omega. And this follows naturally from this definition of L as the cross product of R and P. And it's pretty easy to show that. I'm going to let you see that on your own, or you can find that in the textbook. So I just take the moment of inertia of some rotating rigid body, that's I, and I multiply it by its angular velocity omega, and I get its angular momentum L. And remember this direction of the omega vectors described by the right hand rule. I curl my fingers in the direction of the rotation, and my thumb points in the direction of this angular momentum vector. That's the same direction that this cross product L is going to point. Now, the reason why this angular momentum concept is so useful is that in the absence of external torques, the angular momentum of a system is conserved. So if we look down here at our equation, torque equals dl dt, well, if torque equals 0, then dl dt equals 0. If the derivative of some quantity with respect to time is 0, that means that quantity is conserved. So if torque equals 0, angular momentum is conserved. Just like if external force equals 0, linear momentum is conserved. That's what we learned in chapter 9. So if the external torque equals 0, angular momentum is conserved. Let's answer a conceptual question using this basic idea. So a student is holding two weights out at their sides as shown in the diagram at right. They are rotating in a chair with an initial angular velocity omega initial. They then pull the weights in close to their body. Which of the following statements about the final angular velocity omega final is true? Is omega final greater than omega initial, equal to omega initial, less than omega initial, or does it equal 0? So take a minute and see if you can use this concept of angular momentum conservation to answer this question. Pause the video and come back when you think you have an answer. Okay, so first of all, as the student spins around in the chair, as long as there's no friction in the bearings of the chair, they're spinning around frictionlessly, there will be no external torque on this system of the student with the weights. They'll just spin around without an external torque, so angular momentum should be conserved. That means that L initial should equal L final. That's all angular momentum conservation means. Well, we have an equation for the angular momentum in terms of the moment of inertia and the angular velocity. That is, L initial equals, well, just in general, L equals I times omega. So, L initial is going to be I initial times omega initial. L final is going to be I final times omega final. So why do I have I initial and I final? Isn't I some property of the system that doesn't change? Well, I can change. In this case, as the student pulls the weights in from far away from their body to close into their body, their moment of inertia changes. Because remember, moment of inertia depends on the distribution of the mass in a system. The moment of inertia of a system, I, equals, well, one way we can write it is as the sum of all of sum over some index I of all of the m, I, r, I squared. So I add up all the masses times their distance from the center of rotation squared, and I get the moment of inertia. So as they pull these weights in closer to their body, their moment of inertia changes. There's an initial moment of inertia and a final moment of inertia. So based on this fact, see if you can figure out what is the relationship between the initial angular velocity and the final angular velocity of this spinning student. Pause the video and come back when you think you have an answer. So let's solve this equation for omega final. Omega final is going to equal omega initial times I initial over I final. And the moment of inertia increases as the distance of mass increases. The farther the mass is from the center of rotation, the bigger this r is in our MIR squared equation, the bigger the moment of inertia is going to be. So we know that I initial is greater than I final. This means that I initial over I final is greater than 1, and this means that omega final, if I just take the magnitude of this omega final, it's going to point in the same direction. Students going to keep spinning in the same direction, but this omega final magnitude has to be greater than the magnitude of omega initial. So as they pull these weights in close to their body, they speed up. And if you have a spinny chair at home, if we were on campus, I would do a demonstration of this in class. But if you have a spinny chair at home, you can try this yourself very carefully. Spin around in the chair and hold your arms and legs out in that spinny chair, and then pull your arms and legs in, and you'll spin faster when you pull your arms and legs in. This is a consequence of conservation of angular momentum. So the right answer here, of course, is A. Omega final is greater than omega initial. Another classic demonstration of this effect is a spinning ice skater. So let's watch a video of what YouTube says is the world record for the RPMs of a spinning ice skater. So she spins around, pulls her arms and legs in, and spins at 308 RPM, 308 revolutions per minute, a new world record. So let's watch it one more time and see what happens. She's skating, she's building up some linear momentum, which she converts into angular momentum with her arms and legs out, so she has a big moment of inertia. She pulls them in, her moment of inertia decreases, which means her angular velocity has to increase in order to maintain the same angular momentum, in order to conserve angular momentum. So once again, spin, low angular velocity, big moment of inertia. Moment of inertia gets small, angular velocity gets big. That's the basic idea. So you'll have some homework problems where you put this idea into practice. You actually calculate how the angular velocity changes as you change the moment of inertia. But the concept here is quite simple. Another type of problem that we can solve now that we have angular momentum is collisions between extended rigid bodies. Just using linear momentum, we could only solve problems that involved collisions between point particles, and we modeled all collisions as happening between point particles. But now we can model collisions between rigid bodies. And so one example of a problem we can solve using angular momentum is the collision between a baseball bat and a baseball. So in this problem, a bat with a mass of 1 kilogram and a moment of inertia I equals 0.02 kilogram meters squared has an initial speed v initial bat equals 30 meters per second. It hits a ball sitting on a tee with a mass m equals 150 grams. The bat hits the ball a distance d equals 5 centimeters from the center of mass of the bat. The ball has a final velocity, v final ball equals 40 meters per second, in the same direction as the bat's initial velocity. So if the bat is going in this straight up direction, like this, the final velocity of the ball after the bat hits it is straight up like that. So we want to find the final velocity of the bat, the final angular velocity of the bat, and what percentage of kinetic energy is lost in this collision. Okay. So for part A, if we want to find the final velocity of the bat, well, all we need to do to find that is use conservation of linear momentum. So we have, let's call it P final bat plus P final ball equals P initial bat plus P initial ball. These are all vectors. So I'm going to define a coordinate system here. This center of mass of the bat, right at the instant the bat hits the ball, will be the origin of my coordinate system. And I have an x-axis like this, a y-axis like that, and my z-axis will then point out of the page. Okay, so first of all, the ball is initially sitting on a t, so its initial momentum is just 0. The final momentum of the bat is going to be the mass, big M, times v final bat, plus the final momentum of the ball is going to be little m times v final ball, and this equals the initial momentum of the bat, which is the mass of the bat, times v initial bat. Okay, so we can solve this for v final bat. We get v final bat equals v initial bat minus the mass of the ball over the mass of the bat times v final ball. Okay, so if I plug my numbers into this, v initial bat, well, the bat is moving in the y direction with an initial speed of 30 meters per second, so this is going to be 30 meters per second j hat, minus the mass of the ball is 0.15 kilograms over the mass of the bat is 1 kilogram, times the final velocity of the ball is 40 meters per second j hat. So this, plugging this all into the calculator, is 24 meters per second j hat. The bat slows down a little bit in this collision. It slows down from 30 meters per second to 24 meters per second when it hits the ball. Okay, so we got part A. Now part B, the final angular velocity of the bat. The bat doesn't just slow down when it hits the ball, it also starts to spin a little bit after it hits the ball. So let's figure out what this final angular velocity is. For part B, we're going to use, instead of using conservation of linear momentum, we're going to use conservation of angular momentum. So we have L final bat plus L final ball equals L initial bat plus L initial ball. Okay, so a few things. First of all, we have two formulas for angular momentum. We have L equals I omega, and we have L equals R cross P. So this formula, L equals R cross P, works well for a point particle, which would be like our ball here is like a point particle moving through space around in some coordinate system. And this I omega works well for a spinning object, for a spinning rigid body. So we're going to use that for the bat. Now, for the initial angular momentum of the bat, well, the bat isn't rotating before it hits the ball. And if we treat the bat as a point particle, its momentum is right at the origin of this coordinate system. The initial momentum of the bat, this is P initial bat, is right at the origin of the coordinate system. So that means this R vector is 0 for the bat before it hits the ball. So we can say that the initial angular momentum of the bat is just 0. And the initial angular momentum of the ball is also 0 because the ball's not moving when we start. So the initial angular momentum of this system is just 0. So to find the final angular momentum of the ball, well, This is our r vector that connects the origin of our coordinate system to the ball. That's r. The bat is still, the center of mass of the bat is still at the center of the coordinate system, so we can still ignore its angular momentum as a point particle, but it starts rotating after the collision. So L final of the bat is just going to be I, the moment of inertia of the bat, times omega final bat. The subscript omega final bat. The final angular momentum of the ball is going to be r cross p. Remember, I can write this as r perpendicular times p, where the magnitude of this is r perpendicular times p. And in this case, you can use the right hand rule to figure out the direction of this vector. If I take r, curl my fingers in the direction of b, my thumb points out of the page, which is the z-axis, so this is in the k-hat direction. And r perpendicular here, well, it's the component of r that is perpendicular to the final momentum of the ball, which is just this. R perpendicular is just d. That's the perpendicular component of r. It's the component of r that lies along this x-axis. So I can just write this as P final ball times d in the k-hat direction. Well, the final momentum of the ball is just the mass of the ball times the final velocity of the ball times d k-hat direction. This all has to add up to 0. Okay, so now I can solve this for the final angular velocity of the bat, omega final bat. This is going to equal negative m v final ball times d times k hat divided by the moment of inertia of the bat, I. If I plug in my numbers here, I get that this equals negative. The mass of the ball is 0.15 kilograms. Final velocity of the ball is 40 meters per second. D, the distance from the center of mass of the bat that the ball hits, is 5 centimeters, 0.05 meters. And I divide this all by the moment of inertia of the bat, which is 0.02 kilogram meters squared. This all points in the k-hat direction. And what I get is negative 15. My units here, well, kilograms cancel, meters squared cancel. I just get 1 over seconds, which I can write as radians per second, k-hat. This angular velocity in the negative k-hat direction means the bat rotates clockwise like that, which makes sense. If you hit the ball to the right of the center of mass of the bat's going to spin clockwise after you hit the ball. So notice something important. This final angular velocity of the bat is proportional to d, the distance from the center of mass where the ball hits the bat. If you hit the ball right at the center of mass, the bat doesn't want to spin after the collision. And that's the ideal way to hit the ball. You will transfer as little energy as possible into the spinning of the bat, which doesn't really do anything for you, and as much energy as possible into the final velocity of the ball. So hitting the ball with the center of mass of the bat, that's often called the sweet spot on the bat, that's where you want to hit the ball. If you hit it there, the bat won't spin, you won't lose any energy to rotational kinetic energy of the bat. So this is our final answer. Omega final bat equals minus 15 radians per second k-hat. So we used conservation of linear momentum, that is, we used conservation of p to find the final velocity of the bat. We used conservation of angular momentum, conservation of L to find the final angular velocity of the bat. And now we're going to find out how much kinetic energy is lost in the collision. Well, to do that, we have to calculate the initial kinetic energy, which is just going to be 1/2 mass of the bat times v initial bat squared. If we plug our numbers into that, that's 1/2 of 1 kilogram times 30 meters per second squared, which equals 450 joules. That's our initial kinetic energy. Our final kinetic energy is going to be 1/2 mass of the bat, v final bat squared. That's the translational kinetic energy of the bat, plus 1/2 I, moment of inertia of the bat, times omega final squared. It's the final angular velocity of the bat, the final rotational kinetic energy of the bat. And then plus 1/2 m, mass of the ball, times v final ball squared. Plug in my numbers. 1/2 of 1 kilogram times 24 meters per second squared plus 1/2 of 0.02 kilogram meters squared times 15 radians per second squared plus 1/2 of 0.15 kilograms times 40 meters per second squared. Pop that all in the calculator and I get 410 joules. And then to find the percent kinetic energy lost, well, this is going to be K initial minus K final. That's the amount that I lost in the collision, divided by K initial, that's the amount I started with, times 100%, which equals 450 joules minus 410 joules over 450 joules times 100%, which is about 8.9%. So I lost about 8.9% of my kinetic energy in that collision. So what happens here is that my initial kinetic energy, which is the translational kinetic energy of the bat, gets split three ways. I have the translational kinetic energy of the bat after the collision, the rotational kinetic energy of the bat after the collision, and the translational kinetic energy of the ball after the collision. And of course, your goal in hitting a ball is to get as much of this energy in here as you can. But you're always going to lose a little bit because this won't be a perfectly elastic collision. In this case, we lost 8.9%. So you can kind of see now how you can use angular momentum to fully characterize collisions between rigid bodies. And you have a couple homework problems where you'll look at this in more detail.